Hello everyone. In this video, I'm going to solve problem number 1.20 revised from the chapter 1 from your book. The statement of the problem is liquid fuel is being transported in a pipe. So fuel is entering at a temperature of 10 degrees, going through this pipe and coming out from the T out is not given, but given, I'll tell you what it is. And 18 kilowatts of heat is added to the pipe externally. So the volume flow rate that's necessary to keep the fuel temperature below flash point to be determined. What is flash point? Flash point is where at that temperature fuel self-ignites. So because of fuel is passing through, heat is being added externally, the temperature of the fuel going out is higher, and the question is what volume flow rate is required to keep this temperature T out below flash point. That is what it is. And assumptions are steady state condition exists, specific heat and density are constants, and he gave you the values of specific heat and density. And the question being asked is what is the volume flow rate? So because the mechanism is because the fuel is being transported, where the heat is being added to the fuel from external sources, and the temperature of the going out of the fuel is higher than what is entering in, and we want to make sure the fuel that is coming out has to be below 17 degrees. So I captured some of the details. I'm going to move this paper, my workout paper on the top here, so that I can write the equations. So the rate of heat added to the fuel, that is Q, and that is equal to, the formula for that is mass flow rate times specific heat times delta T. So flow rate is defined in two different ways. One is mass flow rate, and the units for that is kgs per second. And fluid is also defined as volume flow rate, meter cube per second. Makes sense, right? Meter cube is volume, so meter cube per second, kgs per second. So the relationship between mass flow rate, unit flow rate is mass flow rate is density times volume flow rate. So what we'll do is, because we are interested in determining the volume flow rate, we'll rewrite this equation to volume flow rate. Equal to Q. So going back again, in terms of volume flow rate, the same equation, Q divided by rho Cp delta T. And this is the equation for volume flow rate, but we want to make sure our temperature of the flash point is 17 degrees, and we want to keep it below. So as a result, we wanted to have more flow going through that. So we'll say it has to be greater than Q density Cp delta T. So let's plug the values. Flow heat is given. Heat is 18 kilowatts. And density is 788 kgs per meter cube. Cp is constant specific heat is 2.515 kilojoules per kg. Just remember everything is in kilos, kilowatts, kilojoules, kilo, and the delta T is temperature. We know the T out is 17 degrees minus T in is 10 degrees centigrade. So this is the equation to find the volume flow rate. So if you simplify this, it comes up to be volume flow rate is greater than 0.01229 meter cube per second. So that is the question asked, and here is the answer. So going over one more time, heat flow rate is mass times specific heat times delta T, and rewriting the equation in terms of volume flow rate, rho times volume flow rate Cp delta T. Our interest is to find the volume flow rate, so we pull the volume to the left hand side and rewrite the equation, and we wanted to make sure this the volume flow rate has to be greater than, so by simplifying. So this is the answer. Okay, I hope you understood this.